Some black holes weigh about as much as a single star. Others are so massive they sit at the center of galaxies and control the motion of billions of stars. And then there are black holes we've never actually seen, because they may exist only in theory, objects so extreme they push our understanding of reality to its limit. In this video, we're climbing through 5 levels of black holes, starting with the ones we've observed and ending with the ones that might live at the edge of physics. Each level gets bigger, stranger, and harder to explain. And the weirdest part is this: up close, black holes don't just pull on space, they change how time itself flows. But first, what is a black hole? At the simplest level, it's a region of space where gravity becomes so strong that nothing can escape, not even light. The boundary is called the event horizon. Think of it as the point of no return. Cross it, and to escape you'd need to move faster than light. Outside the event horizon, though, a black hole's gravity works like the gravity of any other object with the same mass. That's why black holes are not cosmic vacuum cleaners that suck in everything from far away. If the sun were replaced by a black hole with the same mass, Earth would still orbit almost the same way. The danger begins only if you get close enough for the gravity to become overwhelming. And what happens near that line is where things get truly weird. A helpful way to picture it is this: take the sun and squeeze its mass down into a sphere only a few miles wide. The mass is the same, but the space it occupies is much smaller. That makes the gravitational field near it incredibly intense. Space and time bend sharply. Light tries to leave, but the curvature becomes so steep that every path back out curves inward. That's why the black hole looks black. It isn't made of darkness. It's a trap made by gravity and geometry. Keep that idea in mind, because the first level is the one we can actually catch in the act. Level 1 starts with stars. A star is a long battle between gravity pulling inward and nuclear fusion pushing outward. For most stars, that balance lasts a very long time. But for very massive stars, the fuel runs out, fusion slows, and the outward pressure collapses. Gravity takes over. The core falls in on itself. The outer layers can explode in a supernova, and if the core that remains is heavy enough, it collapses into a stellar black hole. Stellar black holes usually have masses between about 3 and a few dozen times the mass of our sun. What's hard to imagine is how small they can be. A black hole with 10 solar masses can have an event horizon only a few dozen miles wide. That's a city-sized region holding the mass of multiple stars. Near it, gravity is so strong that it can warp the paths of light and make time run noticeably slower compared to far away. So how do we find something that emits no light? We look at what it does to nearby matter. If a stellar black hole has a companion star, it can pull gas off that star. The gas doesn't fall straight in. It spirals into an accretion disk, heats up to millions of degrees, and shines in X-rays. That glow can be brighter than anything else in that part of the sky, even though the black hole itself stays invisible. Those X-rays can be detected by telescopes in space. Another clue is the motion of stars. If a visible star is orbiting an invisible object, and that invisible object is too massive to be a neutron star, a black hole becomes the best explanation. And the most surprising part is that we can also detect black holes without using light at all. We can do that through gravitational waves. When 2 black holes orbit each other, they send ripples through spacetime. Those ripples carry away energy, the orbit shrinks, and eventually the black holes merge. In 2015, LIGO detected gravitational waves for the first time. It was a new kind of astronomy, and it proved that black hole collisions are happening throughout the universe. One early famous example is Cygnus X1, a powerful X-ray source that turned out to be a system with a massive star orbiting an unseen companion. The companion's mass was too large to be a neutron star, and over time Cygnus X1 became one of the strongest early cases for a stellar black hole. Even Stephen Hawking once joked that he bet it wasn't a black hole, and later admitted the evidence was overwhelming. If stellar black holes exist and supermassive black holes exist, there's an obvious question: where are the middle-sized ones? That opens the door to level 2, intermediate mass black holes. These would be black holes roughly between 100 and 100,000 solar masses. They sound obvious, but they're surprisingly hard to confirm. And that's what makes them dangerous to ignore. Without them, the whole story of how giant black holes formed has missing pages. The reason they're missing could change how we think the first galaxies formed. They may be the missing link that explains how black holes grow from stellar size into the giant monsters at the centers of galaxies. Intermediate black holes might be difficult to spot because many of them may be quiet. If they aren't feeding on gas, they don't glow. So astronomers hunt for indirect clues. One place to look is dense star clusters. If an intermediate black hole sits in the center, its gravity should affect the speeds and orbits of nearby stars. By measuring those motions, scientists can infer whether a hidden massive object is present. Another place to look is dwarf galaxies, which may host black holes that are bigger than stellar ones but smaller than supermassive ones. Astronomers also watch for rare events where a black hole tears apart a star that wanders too close, creating a bright flare that can hint at the black hole's mass. One well-known candidate often discussed is HLX-1, which may sit in the intermediate range. Many candidates have been found, but this level remains a major puzzle, and solving it could help solve the next level too, because level 3 is where the scale jumps again: supermassive black holes. These are black holes with masses ranging from millions to billions of solar masses. Evidence suggests that most large galaxies have one at their center, and these black holes may play a major role in shaping their galaxies. In the center of the Milky Way is Sagittarius A star, a supermassive black hole with about 4 million solar masses. We can't see it directly, but we can track stars orbiting an invisible point at incredible speeds. Their orbits reveal the mass and size of the object they're circling. The only explanation that fits is a supermassive black hole. Another famous example is the black hole in the galaxy M87, with a mass around 6.5 billion solar masses. In 2019, the Event Horizon Telescope released the first image of a black hole's shadow, a bright ring of glowing gas around a dark center. It was the first time humanity saw direct evidence of an event horizon region. But supermassive black holes create a huge mystery. How did they form? No star can collapse into something millions of times the mass of the Sun. So astronomers think they either grew over time by feeding and merging, or formed through direct collapse of giant gas clouds in the early universe. Another possibility is that they started with unusually heavy seeds, which brings us to level 4. Level 4 is primordial black holes, hypothetical black holes that may have formed in the first moments after the Big Bang, before any stars existed. The early universe was hot and dense, and it contained tiny fluctuations in density. If some regions were dense enough, gravity could have collapsed them directly into black holes. If these primordial black holes exist, their masses could range widely. Some might be tiny in size yet have the mass of a mountain. Others could be much larger. They would be extremely difficult to detect because they wouldn't necessarily be surrounded by glowing gas. Primordial black holes matter because they connect to dark matter. Galaxies rotate as if there is more mass than we can see. Something invisible adds gravity. In simple terms, galaxies act like they're wearing an invisible weight belt. Many scientists suspect dark matter is made of unknown particles, but primordial black holes offer an alternative. Maybe some fraction of dark matter is made of black holes drifting through space. But there's one big test that could prove or kill this idea. Scientists search for them using microlensing, watching for distant stars to temporarily brighten as a dense object passes in front and bends their light. And if that test ever comes back positive, it would be one of the biggest discoveries in modern cosmology. So far, we have no direct confirmation, and we've ruled out many sizes already, but the idea is still possible in certain windows. Primordial black holes could also help explain why supermassive black holes appear so early in the universe. We've observed quasars from when the universe was less than 1 billion years old, already powered by black holes, with masses of hundreds of millions or billions of solar masses. Growing that large from typical stellar black holes so quickly is difficult. Primordial black holes could have provided heavier seeds that sped up the process. Now we reach level 5, the most theoretical level, quantum black holes. This is where black holes become a frontier problem in physics. Modern science rests on two theories that are both incredibly successful, but don't fully match when you push them to extremes. General relativity describes gravity and spacetime on large scales. Quantum mechanics describes the world of particles on tiny scales. Near the center of a black hole is where our equations stop agreeing, and we don't yet have a complete theory that unites them. This number is so small that trying to picture it is almost meaningless, so here's the point instead. The smallest scale often discussed is the Planck scale, where the Planck length is around 10 to the minus 35 meters. It's the scale where space itself may stop behaving like a smooth fabric. Some theoretical models suggest that at such scales, microscopic black holes could form, far smaller than an atom. If this level is real, it's not just a new kind of black hole, it's new physics. These quantum black holes wouldn't last long. Hawking radiation suggests black holes can lose mass over time by emitting radiation due to quantum effects near the event horizon. For supermassive black holes, evaporation would take far longer than the age of the universe. But for microscopic black holes, evaporation could be almost instant. A tiny black hole might appear and vanish in a burst of energy. Could quantum black holes exist in reality? Some scientists suggest they could have formed in the early universe at extreme energies. Others speculate that extremely high-energy particle collisions might produce tiny black holes for a fraction of a second, though there's no evidence this happens with current technology. The real importance of quantum black holes is what they represent, a potential clue toward quantum gravity, the missing theory that would unify relativity and quantum mechanics. So across these 5 levels, black holes go from the end stages of massive stars, to elusive middleweights, to galactic anchors, to possible fossils from the birth of the universe, and finally to tiny theoretical objects that challenge the foundations of physics. The deeper you go, the more black holes stop being just objects and start becoming questions. Questions about how matter behaves under impossible pressure. Questions about how space-time bends. Questions about whether our laws are complete. And that's why black holes are so fascinating. They're not only about destruction. They are nature's laboratories, places where the universe turns every knob to the maximum and forces us to see what breaks. Stellar black holes show what happens when a star loses its battle with gravity. Intermediate black holes may reveal how black holes grow. Supermassive black holes shape galaxies. Primordial black holes could connect to dark matter and the early universe. And quantum black holes point to the deepest, unfinished work in physics. So here's the final question. Which level feels the most unbelievable, level 4 or level 5? Just reply 4 or 5 and tell me why. Next, I'll explain what would actually happen if you fell toward a black hole, step by step, without the Hollywood myths.